So the purpose of this lab was to predict the motion of a falling slinky and determine if the bottom of the slinky stays stationary as the top falls. The models used were Tracker to analyze the real-world motion, and then GlowScript to produce a computational model that accurately predicts real-world motion. The principles used were Newton's second law, the force of drag, and the force of gravity. The main result is that the bottom of the slinky stays relatively still as the top falls towards the bottom. The main ideas used in this lab are Newton's second law of motion, the force of drag, and the force of gravity. On the left, we see the force of drag, force of gravity, and net force formulas. And then on the right, we see the momentum update, velocity, and position update formulas. The system in this experiment is the slinky, and the surroundings are everything else. The initial conditions for this experiment. The initial conditions from the video, we have a position of basically 0, 0, 0 meters above the ground, slightly above, but not much. Have initial velocity of 0 meters per second and a mass of 0.28218 kilograms. That's including the mass on the slinky. And then Derek's height, which is where the top of the slinky is 1.75 meters above the ground. And we see all these initial conditions mirrored in the coding in the GlowScript model. The experiment. To capture the motion in Tracker, the Veritasium video, the one that we watched, was imported into Tracker and then analyzed to produce a graph of the bottom of the spring's position over time, which we can see in the screenshot of the Tracker software. The coding. Using the source code provided, I produced a model that predicted the motion of the bottom of the spring as the top fell towards the ground. In the first loop, which is the picture in the top right corner, we see the force of gravity acting on the spring, the force of tension opposing gravity, and the velocity and position update formulas. I will also note that the time interval for the first loop is it's the time that the top of the slinky took to reach the bottom. And then the second loop, which is this bottom right picture, we see the force of gravity, the force of drag, and then the position and update formulas as well. And this time interval is the time that it took the bottom of the slinky to reach the ground. Similarities and differences. As we can see in this image, the Tracker model did a pretty good job of replicating the real-world scenario. There were some slight differences in the predicted versus observed position, but nothing of any real significance. The predicted is the blue line, and the observed is the orange dots. Possible sources of error. 2 potential sources of error in this experiment are human error in placing the tracker points. No one is perfect. And not accounting in the computational model for every force acting on the spring. So what if? Depending on the mass of the weight attached to the spring, we will need to either alter the length of the spring or alter the spring constant so that the force of tension in the spring equals the force of gravity on the spring and mass. Regardless of the weight, we can find a way to keep the bottom of the spring stationary as the top falls. The key takeaway is that force of tension has to equal force of gravity. And what does this mean? The bottom of the slinky remains stationary because the forces in the y direction cancel. The mass on the slinky is trying to pull the bottom of the slinky down, but the force of tension from the spring force of the slinky is trying to pull the bottom of the slinky up. When these two forces are equal, the bottom will not move.